刘俊，
哎，志文，
嗨，你的 apartment 的角度跟上次是完全一样的，
呀，
所以你现在是用同样一张桌子对吧？
对，同样一张桌子，同样一台电脑，
一个角度，
同样一台电脑，同样一个角度。
对，你可以 test。
哦，你是我 test 吗？
你不是要 share screen 吗？
哦，OK，is it working？
可以，yes，
那你能看到我的鼠标吗
可以。
？OK，
你要我怎么介绍你啊？
it's up to you。
有什么特别想要跟大家分享的？
好像没有吧？
你可以 share 你的 screen 没问题，就直接 share。
啊哈，
其实我把你之前的 talk 也 upload 上去了，然后我应该会连续三个 talk 都一起放上去。
连续三个什么叫连续
因为你之前
三个？
给我两个，我没有放在 YouTube，因为那时候是 Zoom recording，没有在 YouTube live，但是我现在有放上去了。
哦，I see，啊
对，
哈，
在 YouTube 上连续三个 talk，
嗯，
非常好，年轻有为的
哦，
research。OK，有句你有特别等谁吗？Cento 也在了，所以还有没有其他人你想要等？
嗯，也没什么。
那我们随时可以 start，我
呀，
直接上。Okay, maybe we can start. Let me also recording. Okay. Welcome everyone. Welcome to Harvard CMSA Quantum Matter in Math and Physics seminar series. Today, we are very honored to have Liujun Zou from Perimeter Institute. Liujun comes originally from Hunan in China, and where there are beautiful mountains in the background that you see. It's known as 奇峰3000秀水800 means they are beautiful mountains, 3,000 of them, and more than 800 beautiful rivers. And then he went to Tsinghua University to study his undergrad, and then previously studied under Professor Cento at MIT for his PhD. Currently, he did his postdoc research at the Perimeter Institute. Today, his topic will be Stiefel liquids, possible non-Lagrangian quantum criticality from intertwined orders. As some of you may already heard some version of the talks by other speakers. Today's talk will have 90 minutes, so you might have more chance to hear more. And please feel free to interrupt and ask questions. Let's welcome Liujun. Take over. Thank you.
Thanks, Jordan. Thanks for the invitation and the introduction. And thank you all for being here. The talk will be based on this paper done in collaboration with Yingchen and Chong. Let me start by this manifesto of quantum criticality. A quantum critical state, either a critical point or a critical phase, is interesting and important to study. There are a few reasons. The first reason is this critical state may be described by some interesting universality class, and this universality class often has an enlarged emergent symmetry. So the setting is we have some macroscopic setup with some macroscopic symmetries, and the IR theory has some emergent symmetries. And you can see the macroscopic symmetries are small and the emergent symmetries are big. And in such cases, it's important to understand how the macroscopic symmetries are embedded into the emergent symmetries. And from this embedding pattern, we can identify the relation between the operators in the macroscopic setup and operators in the effective field theory. Also, due to the intricate interplay among all the low-energy degrees freedom at many critical points, there may be very non-trivial dynamics. For example, the system may lose the quasi-particle description, which makes it interesting. Furthermore, because if we perturb the critical state, we may obtain some other states. So a critical state can be viewed as a parent state of other states. Then if we have a thorough understanding of the critical state, we also have a unified understanding of the nearby phases. Because of all these reasons, it's interesting and important to study quantum criticality. And the topic of this talk will also be about quantum criticality, exotic ones. This is a preview of the entire talk. So I will start by talking about something that's by now already well known. The deconfined quantum criticality is supposed to be a critical point between collinear magnetic order and the valence-bond-solid order. And then I will talk about the so-called U1 Dirac spin liquid, which is supposed to be a quantum critical phase, and it can be viewed as a parent state of some non-collinear magnetic order and the valence-bond-solid state. Then I will generalize these two states to an infinite family known as Stiefel liquids. And in particular, I will talk about the next one. We argue it can arise as a quantum critical phase on triangular lattice or Kagome lattice, and as a parent state of some non-coplanar magnetic order and the VBS order. Okay, let's start from reviewing some lessons we learned from EQCP. And let's first look at some conventional order. And to be concrete, let's look at this square lattice spin 1 system. So this is a square lattice, and at each side there's a spin 1 moment. And the Hamiltonian of the system may be written in this way. And in this figure, I'm drawing a pattern of near-collinear magnetic order. So the spins are anti-aligned. If we want to describe the universal non-distance physics of this system, we may use this kind of effective field theory, where n is a 3-component vector. And you can see this Lagrangian has a feature. It can be separated into 2 parts. The first 2 terms are the non-interacting part, and the last term is the interacting part. These 2 parts actually play different roles. So the non-interacting part gives us a mean field picture that enables us to understand the phase diagram. For example, here, if this parameter R is very positive, then N has no non-zero expectation value, and we will obtain a frictionless state. And if R is very negative, N will acquire some non-zero expectation value, and the spin rotational symmetry is spontaneously broken, and we have a magnetic state. In between, there's a transition point. This is the non-interacting part, which provides a mean field picture, and the interacting part imposes some fluctuations on top of the mean field. And usually, we can take the fluctuations to be weak at certain energy scale, usually the UV energy scale. And on the renormalization group, the fluctuations may stay weak or become stronger. At the end, the entire theory on the renormalization group flows to some fixed point describing either the phases or phase transition. So from this example, we review this framework, which may be one of the most powerful framework in quantum many-body physics. That is the framework of mean field plus weak fluctuations, and combined with RG. So in the field theoretical language, this mean fieldness means the effective theory is weakly coupled in the UV. Now, I would like to remark that this effective theory only applies to square lattice spin-1 system, but it doesn't apply to spin-1 half system, although we also care about spin-1 half systems. The reason it doesn't apply is because of the so-called LSM type theorems or constraints. Namely, for square lattice spin-1 half system, if we want to preserve all the symmetries like the spin rotational symmetry, time reversal symmetry, and the lattice symmetries of the square lattice, then there's a theorem saying that it's impossible to have a frictionless ground state. However, the previous effective theory does have a frictionless ground state. This means the previous effective theory is not applicable to square lattice spin-1 half system. Now you can ask, if a frictionless ground state is not possible, then what is possible? What is possible turns out to be some different scenarios. First, the system can spontaneously break some symmetries, or it can preserve all symmetries. But if it preserves all symmetries, then the system has to be gapless or develop some topological order. I also want to remark this LSM constraint is actually rather specific. It does not only say it has to be in this case, it says something more concrete. It says, if, for example, if it's symmetric and gapless, then not all types of gapless states are possible. Only some specific ones are possible. And not all topologically ordered states are possible. Only some specific ones are possible. But for now, let's just look at the symmetry breaking scenario and ask what are the possible symmetry breaking states on in this square lattice spin-1 half system. And one obvious option is to again develop some neo-collinear magnetic order where the spins anti-align with each other. That's possible. And we can ask what are the possible non-magnetic states. Then maybe the simplest possible one is this so-called valence-bond-solid state where the C4 lattice rotational symmetry is spontaneously broken. Here are 4 patterns of the VBS with broken C4 lattice rotational symmetry. Each red ellipse represents a spin singlet formed by the spin-1 half moments at these 2 sides. And you can see the lattice C4 symmetry, C4 rotational symmetry is broken, spin rotational symmetry is preserved. And from this figure, you can also kind of see where this LSM constraints come from. In particular, we can ask, suppose we want to start from the VBS order and destroy the VBS order. Is it possible to obtain some frictionless state? And to do so, we may want to proliferate the vortices of the VBS order parameter. And here is a pattern, is a configuration of the VBS vortex. And you can see at the core, there's a dangling spin-1 half of the VBS vortex. This indicates if we really proliferate the VBS vortices, although we can indeed destroy the VBS order, we will develop some magnetic order. And this phenomena where one order is destroyed, the other order is established, we call it the intertwinement between these 2 orders. And from this cartoon, you can also kind of see where this intertwinement comes from. It comes from the spin-1 half nature of the spin moments, as well as the lattice symmetries, the square lattice symmetries. So here we can extract another lesson. That is a UV setting, or in other words, lattice scale physics can sometimes constrain the IR physics or the universal ground state physics, and it may result in some intertwined orders. Okay, now that we know for this square lattice spin-1 half system, there can be the neo state and the VBS state, and then a lateral question is to ask whether there can be a continuous continuous direct transition between them without fine-tuning. And according to the standard Nonenvelope principle, this is not possible because these two states break very different symmetries. For example, this one breaks spin rotational symmetry, but preserves lattice rotational symmetry. This one is the opposite. But people realized that this may still be possible. And initially, the way to understand it is to use this so-called parton trick, where we write the spin operator S as 1/2 the dagger sigma z, where sigma is the standard Pauli matrix and z is a two-component complex bosonic operator. As you can see, this expression has a U1 gauge redundancy, in which if we multiply z by a U1 phase factor, the entire expression is invariant. What this implies is that the effective theory written in this way will actually be an emergent U1 gauge theory that's coupled to Z. So there will be a U1 gauge field A, emergent U1 gauge field A that's coupled to Z. And in terms of a picture, is this picture. So we have some magnum that may be created by some spin reason Wernerian operator S. It fractionalizes into a pair of spinel and anti-spinel Z and Z dagger interacting with the emergent U1 gauge field. So this is a remarkable emergent phenomena. And starting from this Lagrangian, you can see this Lagrangian is also within the mean field paradigm in the sense that you can separate the Lagrangian into the non-interacting part and the interacting part. And then using a Sabina mean field analysis, actually a little bit more involved, one could understand that this Lagrangian can describe both the nil state and the VBS state, as well as the transition in between. Because at the end, it turns out the excitation Z is not deconfined in both phases, but it can be viewed as deconfined at the critical point. That's why this critical point is called a deconfined quantum critical point, DQCP. So this is an interesting emergent phenomena. And from this phenomena, we can also learn some lessons. Yes.
Oh, hi. Okay. Sorry, naive question. Also, audience, feel free to interrupt, even just naive or even uncurious question. So, can you maybe physically or mathematically explain why we choose the U1 gauge field to do this kind of parton constructions instead of other gauge group or gauge fields?
This is subjective. There's no intrinsic reason. You can choose others.
So this can maybe only determined by, for example, energetic by doing numerical simulations. And from kinematical point of view, you can propose whatever you can and perhaps match some total anomaly that you will mention later. Is that just the logic?
I think initially people, I'm not entirely sure, but I think he's here. I think initially this was the most obvious one to come up with. Then they came up with this one, and it had all the next features. We discussed this and that. In terms of precise energetics, at the end, people still need to do the numerical simulations. At the stage of choosing this particular parton construction, people didn't know the energetics.
Yeah, okay, thanks.
Okay, so from here, we can also learn some lessons. The first is that in condensed matter physics, we can use gauge theory to describe some interesting state. And the power of the gauge theory still kinds of relies on the mean field plus weak fluctuation paradigm. So the gauge theory can be viewed as a more powerful, modern version of the mean field plus weak fluctuation paradigm. Furthermore, you can ask this exotic deconfined quantum criticality arises here, but why does it arise here? What's special in this setup? And I guess it's not too hard to convince yourself that the origin is related to the competition between these two intertwined orders. If the orders are not intertwined, then we just have the usual Nonenvelope type transition instead of this kind of exotic transition. But these are all good. But it also comes with a cost. That is, now we are using a gauge theory to describe the system, but gauge theories are complicated, precisely because of the gauge redundancy, and with some operators are gauge non-invariant, some operators are gauge invariant, and at the end, all the physical quantities should be gauge invariant. And in particular, for this 2+1D U1 gauge theory, there's a more complicated story. That is, there's a gauge invariant operator monocle, which is a topological disorder operator. It further complicates the story. Then you may want to ask, is a gauge theoretic description really necessary? After all, we just want to describe a transition between two conventionally ordered states. Actually, you can even ask, is the gauge theoretic description even sufficient? The reason to ask this question is because there's numerical evidence for this transition, and people found for this transition, the effective theory is nearly described by some conformal field theory with an emergent SO5 symmetry. But from the previous gauge theory, it may not be that easy to see where the SO5 symmetry comes from. And to understand all these issues, people proposed many other dual descriptions of the same transition. And the one that's particularly relevant to our talk will be this West-Zumino-Witten description. So the effective action is written here. Here N is a 5-component unit vector. In other words, it lives in the manifold S4. And for the purpose of this talk, it will be useful to note that S4 can also be viewed as SO5 mod SO4. The first term in the action is the usual nonlinear single model action, and the second is the also kind of usual O5 vector West-Zumino-Witten action. It's written here. You don't really need to read it through. And my purpose to write it here is just to show you that it can be explicitly written down. Maybe you want to notice there's a determinant here. So you may want to ask, what's the advantage of this theory or of this formulation? And the first advantage is this is not a gauge theory, so you can clearly identify what's the operator content, what's the physical operator. It's clearly N and the composites of N. Furthermore, you can clearly see how this theory is possibly compatible with an SO5 symmetry, because N has 5 components, the SO5 can just rotate the 5 components. Furthermore, it also has a time reversal symmetry. So the emergent symmetry of the theory is written here. And now we notice the square lattice 1/2 system doesn't have such a big emergent symmetry, it only has some macroscopic symmetries. So it's important to understand how the macroscopic symmetries are embedded into the emergent symmetry. So the SO3 spin rotational symmetry is embedded by rotating the first 3 components of N and time reversal this way. And the lattice Stiefel rotational symmetry, it turns out rotates the last 2 components. So from this symmetry embedding pattern, we can obtain the physical picture that the first 3 and the last 2 components of N can be identified as the Neal and the VBS order parameters. And in this formulation, the tuning parameter is something like this. As you can see, depending on the sign of lambda, the system may either favor Neal state or VBS state. But so far, you may have also noticed I have basically just been talking about the nonlinear single model in general, but not the West-Zumino-Witten description. Then you may wonder what's, yeah.
Yes, sorry, the internet. Just make sure, is time reversal symmetry important here? Can I remove the reversal? Since it's not crucial, is it?
It's not crucial for what?
DQCP in the follow deconfined quantum criticality. Is that crucial? It can be there, but it's not necessary.
To be honest, I don't quite remember. I guess when you say whether it's crucial or not, you are asking if I break time reversal symmetry, whether there will be some new relevant perturbations that's allowed, which is allowed if I have time reversal symmetry. I guess you also impose I guess you also impose at least the SO3 and the lattice symmetries. I don't remember the answer to this question, but I'm sure you can find it in all these papers.
At least from maybe later you will mention the whole anomaly perspective. The anomaly is not protected by time reversal. It doesn't need time reversal, right?
Well, it doesn't need time reversal, meaning SO5 has its own anomaly, but time reversal also contributes to the anomaly. So it's important to keep it.
Okay, but breaking time reversal, you are not sure whether it will affect the discussion later that you are going to say.
Oh, well, it will certainly affect. If it is emergent symmetry and it contributes to the anomaly, it will affect the are you asking, and let me make sure what you're asking. Are you asking, suppose I start from the potential CFT fixed point and I add and I explicitly break time reversal by introducing some time reversal breaking operators, will the theory flow back to the SO5?
Yeah, you can say
and the time reversal symmetric theory? Are you asking that?
Yeah, you can say that way.
I don't remember the answer.
Okay. All right, thanks. Thank you.
Yeah, but in terms of anomalies, it contributes to anomalies, so it's important to keep. Okay. So about the Westminster-Witten term, it's important because it encodes the intertwinement of the orders. In particular, we can analyze the structure of the vortices of the last two components. As we just discussed, the last two components can be viewed as the VBS order parameter. And if you analyze the vortex, you will see at the core of the vortex, there's an effective spin 1/2 formed by the first three components. And this is in precise agreement with our previous cartoon, where the VBS order parameter has a vortex core with a spin 1/2. And from this way, we see it is the Westminster-Witten action that encodes the intertwinement. You may also want to ask, in this formulation, where does the DQCP locate? Just as a usual non-linearizable model, if we make the non-linearizable model coupling G weak, then the system is in the Goldstone phase with spontaneously broken symmetries. But the DQCP is not supposed to be such a state. What this means is, to describe the DQCP, I have to tune this theory to the strong coupling regime. That is to say, this formulation for the DQCP is not mean field-like. And here we can also summarize some features and bugs of the Westminster-Witten formulation of the DQCP. The features is basically that the local operator content and the symmetry are more manifest. And the bugs is basically is not mean field-like, or is strongly coupled at all scales, or is related to that is non-renormalizable. And at this point, you may want to ask, wow, this is a non-renormalizable theory. Are you kidding? What does it mean to say that some state emerges in this non-renormalizable theory? And to answer this question, let's first look at some renormalizable field theories. And let's ask, what's the major advantage of renormalizable field theories? To me, the major advantage is its powerful predictability. Namely, with just a few parameters, we will be able to predict everything in this renormalizable field theory, everything including what we usually refer to as non-universal details. But it also has a disadvantage, that is, if we view this renormalizable field theory as a fundamental theory, then it's fine-tuned. But if we view it as a no-energy effective theory, it's okay. To see it, let's again consider this square lattice spin 1 system. This spin 1 this time for simplicity. And maybe the lattice Hamiltonian is written this way with first label coupling, second label coupling, third label coupling. And there's a schematic phase diagram. So this phase diagram is schematic for illustration purpose. And the phase boundary is not supposed to be taken seriously. So we will have some frictionless state and some magnetic state. And in between, there's a Wilson-Fisher transition described by this. And there's a phase boundary described by the Wilson-Fisher fixed point. But usually we describe the Wilson-Fisher fixed point using the phi-4 type renormalizable Lagrangian. But if you ask along this entire phase boundary, where does the phi4 theory really applies? It really at most applies to some major zero portion. And in almost everywhere, it should be viewed as the phi4 theory, but with some irrelevant perturbations added to it. And the irrelevant perturbations will ruin the renormalizability. That is to say, if I really view the renormalizable description as the fundamental theory, then it's fine-tuned. But if we view it as a learning effective theory, it's okay because the normalization group will tune it for us, will tune the irrelevant perturbation, irrelevant coupling constants to zero for us. Namely, there will be an energy scale below which the renormalizable description becomes effective. And this energy scale can be different at different points on the entire phase boundary, but there is one. Okay. Then we turn to non-renormalizable field theories, and we may ask, what's the main disadvantage of the non-renormalizable field theories? I think it's just the opposite with the renormalizable field theory. That is, if we want to make predictions, we need infinitely many, we need to specify infinitely many parameters, or the parameter space is infinite dimensional. Or in other words, we need to specify infinitely many counterterms in the theory. But does this mean non-renormalizable field theories are not predictable at all? I think they are still predictable, especially they are predictable. They are able to predict universal physics. And to appreciate this, let's first look at another type of theories, lattice models, which are the models that we will use and love. So what's the main advantage of lattice models? I think the main advantage is a lattice model is extremely well defined. We know precisely what the Hilbert space is, we know precisely what operator content is, and we can use the lattice models to predict universal physics. There are hundreds of thousands of papers doing that, and many of them are very good. But it also has some disadvantage. That is, if we want to use lattice models to predict non-universal properties, we also need to specify infinitely many parameters. So here again, we look at this square lattice in one model. In this particular lattice Hamiltonian, I'm just writing down 3 coupling constants. But you really need to also include fourth label coupling, fifth label coupling, exponentially decaying coupling, exponential squared decaying coupling. You need to include everything. So the parameter space is also infinite dimensional. But it's okay if we just want to describe some universal physics, we can fix many of the parameters to some particular value and just vary a few of them, and we can still study the universal physics. So, so from here we can also know what does it mean if I say a state emerges from some non-renormalizable field theory. It means something similar to saying that some phase or phase transition emerges in a lattice model. Namely, although the parameter space is infinite dimensional, there is a parameter regime in which the universal physics emerges. In particular, if we are talking about a phase, then inside this infinite dimensional parameter space, there's a co-dimension 0 parameter regime in which the universal physics agrees with this phase. And if we are talking about a direct continuous transition between 2 phases, then in the infinite dimensional parameter space, there's a co-dimension 1 parameter regime in which the universal physics agrees with the fixed form corresponding to that transition. Okay, then you can ask what is the advantage of a non-renormalizable field theory compared to a lattice model? Then, of course, it's a field theory, so it has more manifest emergent symmetries and possibly anomalies, and also it's easier to treat analytically. Okay, so I want to summarize this discussion.
Just make sure I get a main point. I think you are saying much more than say if I if you have some non-renormalizable field theory, you may try to find a UV completion by lattice. I think you are not saying you are not saying that, right?
No, I'm saying it's legitimate to view a non-renormalizable theory already as the UV theory. Just in a way in which you view a lattice model as a UV theory.
Right. So you don't even need to worry about another lattice UV completion beyond the non-renormalizable field theory. You don't require that. You don't need to consider a deeper UV beyond the non-renormalizable field theory. You are just taking the non-renormalizable field theory as a UV theory.
I will do that later, but sometimes it's possible to have an even more UV completion of the non-renormalizable theory, either in terms of some renormalizable theory or a lattice model. Sometimes, go ahead.
But are you trying to just view non-renormalizable field theory as a UV completion by itself without even a UV lattice model at a deeper UV? Is that the perspective you are taking in these few slides, which you are trying to explain many subtle points? Very nice, but I just want to make sure with people or I get the main point.
Yeah, that can be viewed as the perspective. Yeah.
Huh?
That can be viewed as the perspective, but it's still nice to find at least, let's say, a lattice model description as the UV completion of the non-renormalizable field theory.
But you are saying that even without UV, without lattice, you still try to view the non-renormalizable field theory as a UV completion by some way.
Yeah, maybe let me really use this cartoon. I think this cartoon will answer your question. So what I try to say is that a non-renormalizable field theory, in some sense, is in between a lattice model and a renormalizable field theory. In the sense that it's a field theory, so the emergent symmetry is more manifest and is easier to deal with analytically. But it's also like a lattice model in which the parameter space is infinite dimensional. In particular, if we look at this, this particular example, we can either use this lattice Hamiltonian or this renormalizable field theory or this non-renormalizable nonlinearizable model to describe the same universal physics in which we have two phases, namely the frictionless state or the magnetic state, and in between there's a transition. What's important here is to go from one state to the other, we just need to tune a single parameter. This single parameter may be expressed in a very complicated way in terms of the parameters appearing in the lattice Hamiltonian or non-renormalizable field theory, but it's a single parameter. In particular, I view all of these three as legitimate UV descriptions of this universal physics in this talk. Okay. Maybe this is a non-digression and you already forget about the license agreement from DQCP. So let's recap. So first, we reviewed this powerful framework in quantum manifold physics. That is the framework of mean field plus weak fluctuations. The mean field may be conventional or gauge theory like. Secondly, we reviewed the LSM physics, namely the UV settings may constrain the IR physics and it may result in some intertwined orders. Third, we discussed that due to the competition between some intertwined orders, we may find some exotic quantum criticality. Finally, we discussed this Westminster-Witten formulation of the DQCP. It has some features and bugs. Now, we want to ask some questions. The first question is, can we find a more exotic quantum criticality? Maybe also in the vicinity of some intertwined orders. And in particular, all the quantum critical states we have discussed so far in this talk are still within the paradigm of mean field plus weak fluctuations. The mean field may either be conventional like or parton like. So we can ask whether we can go beyond this paradigm. And in field theoretic language, this question is to ask whether we can find non-Lagrangian archifixed points or intrinsically non-renormalizable archifixed points, namely archifixed points that cannot be described by any weakly coupled renormalizable Lagrangian at any scale. And let me emphasize the examples discussed so far are not non-Lagrangian, although some of them have non-renormalizable descriptions. They are not intrinsically non-renormalizable because they still also have renormalizable descriptions. To be non-Lagrangian here, it has to have no renormalizable description. Okay, and before going further, let me first mention why are non-Lagrangian theories interesting. And there are many reasons, of course. And the first one is just it opens up new landscape of quantum manifold states. Here, I would like to make a comparison between this and the discovery of n equal to 3 supersymmetric field theories. I learned this from an interesting slide by Yuji Tachikawa for what is common field theory. I recommend this slide. And so initially, people thought there could be supersymmetric field theories with n equal to 2 and 4, but not n equal to 3. The reason was based on the assumption that the theory will have a Lagrangian description, and the people wrote down the Lagrangians with people could write down Lagrangians with n equal to 2 and 4. But when people tried to write down a Lagrangian with n equal to 3, people found that the Lagrangian automatically had n equal to 4. So people concluded n equal to 3 supersymmetric theories could not exist. But later in this paper, people found using other way by going around the assumption that the theory has to have a Lagrangian description. It's actually possible to have n equal to 3 supersymmetric theory. So it also opens up some new landscape of quantum many-body states. The situation is kind of similar. Furthermore, if such states can be identified, it will challenge established frameworks and inspire new ones to study them. For example, in the condensed matter language, if we have such states, then we are forced to think about how to study them without a mean field picture. This is our strategy. So usually, the being non-renormalizable or not mean field-like is viewed as a bug of the nonlinearizable model. But now, if we are looking for non-Lagrangian or intrinsically non-renormalizable theories, maybe we can turn this bug into a feature. Furthermore, people noticed that by perturbing another state known as Dirac spin liquid, one can obtain the DQCP. So maybe our strategy can be, we first write down a nonlinear scale model formulation of the Dirac spin liquid, and then we generalize these nonlinear scale models to possibly non-Lagrangian cases. Okay, and this will be, this brings us back to this map. So we have already talked about the DQCP and we learned some lessons. Now we will move to Dirac spin liquid and then we will generalize. That's the plan. So now we go to Dirac spin liquid. Let's have a quick review of the physics of Dirac spin liquid. So this state was initially introduced in the condensed matter literature, also using this parton shape, in which we write S as 1/2 psi sigma psi sigma psi, where this time psi is a two-component fermionic operator, although sigma is still the Pauli matrices. You can see there's still a U1 gauge redundancy, and what this means is that the low energy effective theory will be a U1 gauge theory where psi is interacting with some U1 gauge field A. So the picture is still like this. We have some macron that's created by spin-Wilson Nonlinearizable operator. It fractionalizes into spinel and antispinel, interacting with some U1 gauge field, but this time the spinel and antispinel are fermionic. Furthermore, if at the lattice level we tune the band structure of this psi such that the band structure has some gapless Dirac cones, then the low energy effective theory can be written as a 2D3, 2+1 dimensional U1 gauge theory, coupled to NF flavors of Dirac fermions. In condensed matter literature, the most studied case is NF equal to 4, which will also be the focus of this talk. I want to briefly mention there's numerical and experimental evidence that this state may indeed emerge in some model or material. Okay, now having this theory, we can analyze its properties. Maybe the first question we want to ask is, what's the fundamental local operator in this theory? This state is called a Dirac spin liquid, but the most fundamental local operator is not this Dirac fermion operator because it's not gauge invariant. It turns out the fundamental local operator is the monopole operator. So the monopole operator is the operator that creates 2-pi magnetic flux of this emergent U1 gauge field. And it has a more complicated structure in this theory because there are 4 Dirac cones, 4 Dirac gapless Dirac fermions. So in the background of a 2-pi flux, each Dirac fermion will contribute a 0 mode. And using the reasoning from this paper, we know to have gauging invariant monopole operators, we have to occupy 2 out of the 4 zero modes. And there are 6 ways to occupy 2 out of the 4. That's why the monopole operator has 6 components. So it already has a very rich structure. I also want to remark that the monopole operator cannot be easily written down in terms of the variable appearing in the Lagrangian. This actually makes it a little bit inconvenient. And I have been saying the monopole operators are fundamental. So you may wonder what's fundamental about it. To answer this question, we need to first look at the emergent symmetry of the theory. This theory has a very intricate emergent symmetry. It has some discrete symmetries, which let me just ignore for most of the part. And let's just focus on the continuous symmetry. It's SO6 cross U1 top. More precisely, we also need to model a common Z2 center here, but it's carefully treated in our paper. But here, let me just now mention it. So where does this SO6 come from? Recall the theory has 4 flavors of Dirac fermions. So there's a SU4 flavor symmetry, but the Dirac fermions are not gauge invariant. To ask what the symmetry the system has, we have to ask what operations act faithfully on gauge invariant operators. Then, if we only look at gauge invariant operators, the SU4 turns out to be SO6, and its action is to rotate the 6 components of the monopole. And this U1 top represents topological. Its action is to multiply the monopole by U1 phase factor. This symmetry is responsible for the conservation of the magnetic flux of the internal gauge field. This may also be easy to understand because if we have this symmetry, then we cannot add monopole operators into the Lagrangian because then the Lagrangian will change under the symmetry. And we also said the monopole is what changes the magnetic flux. Now, if we cannot add them, then the flux is conserved. But here, I want to remark that this U1 topological symmetry doesn't come from the flavor symmetry. It comes from this non-trivial mechanism of flux conservation. This observation will be kind of useful later. Now we can understand what I mean by saying that the monopoles are fundamental. They are fundamental in the sense that in this theory, if we write down any gauge invariant local operator, there is an operator that is a composite of monopole operators which have identical symmetry transformation rules as the original operator under the entire emergent symmetry. Because this is supposed to be a critical theory, if these 2 operators transform identically, then we will expect operator mixing and we will expect identical correlation functions at the non-distant distances of these 2 operators. Then we can identify them. For example, if we consider the mass term of the Dirac fermions that transforms in the adjoint representation of the SU4, then it can be identified as this monopole operator, where A is a 6x6 antisymmetric matrix. Okay, and there's also numerical evidence that this theory flows to a non-trivial CFT in the IR.
Can you explain what's the numerical evidence to show the non-trivial CFT? Is there some tracking of the scaling dimension? More details? Can you say a bit more? How is that the? What's the numeric? What kind of check, for example?
I do have to apologize. I cannot.
Sure. All right. Thanks.
Okay. So this is the field theoretical aspect, and now let's look at the condensed matter aspect. In particular, I want to discuss how to view this Dirac spin liquid as a parent state for intertwined orders. So in particular here, we need to understand what are the order parameters of the intertwined orders. And to understand that, it's important to understand how the microscopic symmetries are embedded into the emergent symmetry. For concreteness, let's consider triangular lattice in one half system. It turns out this embedding pattern is rather non-trivial to be worked out, but people did impressive work and did work it out. The full answer is quite lengthy to be quoted, so I'm just giving some example here. For example, the SO3 spin rotational symmetry just rotates the first 3 components of the 6-component monopole. And you can also see from these papers how the lattice symmetries act. And at the end, you can conclude that the first 3 and the last 3 components of the monopole can be viewed as magnetic and VBS order parameters respectively. Then to view this Dirac spin liquid as a parent state, to obtain these 2 other states, what we can do is to add some mass term to the Dirac spin liquid. And depending on what kind of mass term we add, the system may either develop some non-collinear magnetic order, where the expectation value of M1 to 3 is non-zero, or it develops some VBS order, where the expectation value of M4, 5, 6 is non-zero. And you already see some curious features here. First is adding mass to the Dirac fermions seems to be a rather mundane operation, but it makes monopoles have non-zero expectation value. And monopoles are supposed to be some complicated object. So how can this happen? And also, why do we naturally obtain a non-collinear magnetic order instead of a simpler collinear magnetic order? So these are some curious features, and people could understand them from the perspective of the gauge theoretic description. Here, I want to provide a simpler understanding. And again, we want to ask whether a gauge theory description is necessary for this state. To answer this question, let me first introduce 2 other concepts. The first is this Stiefel manifold, is the manifold SON mod SO4, where n is equal to or greater than 5. And an element of this manifold can be parameterized by little n, which is an n by n minus 4 matrix with orthonormal columns. And then it turns out on this manifold, one can write down a Westminster-Witten action in 2 + 1D in this form. Again, you don't need to read it through. And the main information I try to convey here is that the Westminster-Witten action for any n is a direct generalization for the one for n equal to 5. And the one with n equal to 5 is relatively well known is the O5 vector Westminster-Witten action. Maybe you can see the similarity, and both of them have some determinants. Then there's the claim. The claim is the Dirac spin liquid is equivalent to this Westminster-Witten nonlinear signal model on the Stiefel manifold SO6 mod SO4 with this action. The first term is the standard nonlinear signal model action. The second term is this Westminster-Witten action with n equal to 6. Here, this n is a 6 by 2 matrix, and it precisely represents the 6-component monopole. Or in other words, actually, the 2 columns of n are the real and imaginary parts of the monopole. So again, let me mention what I mean by equivalent here. Strictly speaking, this is a kinematic statement, meaning these 2 theories have identical symmetries and anomalies. But dynamically, we also propose that by tuning the parameters of this nonlinear signal model, there will be a parameter regime in which the identical universal physics as the Dirac spin liquid emerges. I will not go through the argument here, but you can see it from our paper. I just want to show a simple application of this nonlinear signal model description. And that's to answer the question, why do we obtain a non-collinear magnetic order from the Dirac spin liquid? Initially, it was understood by Stiefel and Fischer within the gauge theoretic formulation, and they invoked the quantum spin-Hopf physics and the particle vortex duality. It's a very elegant argument, but also a little bit complicated. But now, using the nonlinear signal model description, it may be much easier to understand because we just said n is just the monopole, and the monopole, the first and the second 3 rows of the monopole are the magnetic and the VBS order parameters. So now, suppose we develop some magnetic order by giving n some non-zero expectation value. Because the columns of N are orthonormal, then the expectation value may take this pattern. And if we just look at the first three rows, you see we have two orthonormal three-component unit vectors as our magnetic order parameter. This is precisely the order parameter for non-collinear magnetic order. And in this way, we see it's very natural to obtain non-collinear magnetic order from the Dirac spin liquid. This is also a sanity check that this description is indeed also another valid description of the Dirac spin liquid. And you also, maybe you have observed, here we have non-collinear magnetic order because N has two columns. And you can naturally wonder what if N has more columns where we have more complicated magnetic order. For example, if N has three, where we have non-coplanar magnetic order. That's indeed the case. And that's the content of the next part. Now we want to generalize Dirac spin liquid and the DQCP to an infinite class, which we call Stiefel liquids. So let me describe it. So each Stiefel liquid is indexed by two integers, n and k. K is just a non-zero integer, and n is an integer that's equal to or greater than 5. The effective action is written in this way, where n is an element in the Stiefel manifold, SON mod SO4. That's why it's called a Stiefel liquid. So it's an n by n minus 4 matrix with orthonormal columns. The first term in the action is the standard nonlinearizable model action. The second one is the Wess-Zumino-Witten action for that particular n multiplied by a level k. And now with this effective action, we can analyze its properties. First, what's the fundamental operator? It's very clear, it's just this n. And we can build up a composite of n. Then let's ask what's the symmetry. Again, it has some interesting discrete symmetries, which I will not talk too much about. And let's just look at the continuous symmetry. And there's a SON continuous symmetry acting by left multiplication, and SON minus 4 symmetry acting by right multiplication. So this is a huge emergent symmetry. Furthermore, what's special to this class of theories is about their relations. So there's a cascade structure between different Stiefel liquids. For example, if we look at this matrix N, which is n by n minus 4, if we fix one of its entries, say in the first column and the first row, V1, and then the matrix reduces to this form, and you can see this n prime matrix, which is n by 1, n minus 1 by n minus 5 matrix, still satisfies the condition that the columns are orthonormal. In other words, n prime lives in the Stiefel manifold SON minus 1 mod SO4. And if we plug in this configuration into this action, we will see this action precisely reduces to this one, namely K is invariant, capital N is reduced by 1, and the field N is replaced by the reduced matrix n prime. What this means critically is that if we perturb a Stiefel liquid with a larger n, we can obtain a Stiefel liquid with a smaller n. That's why we call it a cascade structure. In particular, if n is 6, it means if we perturb the Dirac spin liquid, we can obtain the DQCP. This relation between the Dirac spin liquid and DQCP was noticed within the H-theoretic language, again using a more complicated way, but from here you see it's more transparent. Okay, we can also analyze the anomaly of the Stiefel liquids. So the anomaly is an obstruction to happen in the system to gauge fields corresponding to the emergent symmetries. And to characterize it, we can view this theory as the boundary theory of some high-dimensional SPT. In particular, we can view this 2 plus 1D Stiefel liquid as the boundary of a 3 plus 1D SPT, whose protecting symmetry is precisely the emergent symmetry of the Stiefel liquid. And then we can use the topological partition function of this SPT to characterize the anomaly of the Stiefel liquid. And the topological partition function is written here in terms of various Stiefel liquid classes of the gauge fields corresponding to the emergent symmetry. Again, it's written here just to show you that it can be written down. You also don't need to read it through, even if you are kind of unfamiliar with such quantities. You can just view it as a generalization of the theta term that describes the response of a topological insulator. And we also did some simple Lagrangian analysis and found some evidence that when n is sufficiently large, the theory can describe some non-trivial CFT. Now let's recall the numerical evidence that when n is equal to 5 or DQCP, the theory is nearly conformal. And when n is equal to 6 or Dirac's liquid, it's very likely conformal. So we just propose for all n larger than 5, the theory corresponds to some non-trivial interacting CFT. Okay. Now, yeah.
Maybe basic, but I think it's time to ask. Let me see how to start with. Actually, maybe just from the slide of anomaly, when you show the multiple anomaly, can you say a few words? Because earlier you are trying to say the monopole, monopole, maybe play some role, but can you say a few words how that has anything to do with the anomaly here? So let me clarify that. Sorry if these are too boring questions, but I think it's good to ask. So magnetic monopole here actually is a zero-dimensional object in 2+1D. 3D, is that right? It's more like instanton, right? And actually, earlier discussion of monopole kind of too quick. I wasn't really sure whether I follow, but can you say a few words how the anomaly constraint come in related to the monopole part? Is there something you can say? For example, maybe the quantum number monopole. Maybe you already said, but I wasn't sure what I can connect to what you have for the anomaly.
So let me just make sure by monopole, you are referring to the specific case where n is equal to 6 and we have the Dirac's liquid.
Oh, I suppose you have a several case, n equal to 6, n equal to 4, n equal to 6, n equal to 5. Either case, if this is a general formula for, this is for formula for n equal to 5 and 6, correct?
For n.
Yeah, great. So then you can consider monopole in any case.
Strictly speaking, for any odd n, for any even n is more complicated than this, but we can ignore that issue here.
Sure.
So I wouldn't say the particular quantum number of the monopole plays a lot of role in determining this anomaly, because maybe now it's useful to go back here. So the monopole is precisely this n here. In this formulation, monopole is just this n. If you are, so the symmetry quantum number of n just tells us what is the symmetry. That's all. It doesn't tell us about the anomaly. It's this Westminster-Witten action that tells us about the anomaly. Does this answer your question?
Well, yes. That's actually true. Okay. But let me ask. Actually, this is really basic. Sorry for boring. Maybe for some audience. But people talk about monopole. But when you say monopole, do you really think that's a magnetic monopole for some U1 gauge theory, or you actually does not require that? Because that's a terminology I think also possibly confuse some other people. Why don't you just call maybe some instanton 0D of 2+1D space-time, or maybe call it a hog if you consider some configuration. Why call monopole here?
Let me call the instanton. I mean instanton.
No problem. Right.
Okay.
I just want to make sure whether there's some additional sectors you introduce to make it a magnetic monopole, some monopole type, which I'm not.
No.
But I think if you introduce the U1 gauge theory near the quantum critical point, that's indeed a magnetic monopole, right? Except you don't necessarily need to have a U1 gauge theory. Hello?
What do you mean?
Sorry, what do I mean? I mean that magnetic monopole, usually you need to specify the gauge group, maybe a gauge group sector. For example, there's the electric sector, there's the dual magnetic sectors. Usually magnetic monopole means the endpoint of some total line of some gauge group, right? And here you don't mention that, so that's why I asked, what do you mean by monopole?
Oh, I guess you are referring to the 3+1 D you want to say. Perhaps the terminology here is a bit confusing. Here for 2+1 D you want to say, when I say monopole, I really just mean the instant.
Right, yeah. Okay.
Okay.
Yeah, thanks.
Okay. So, so far we have talked about this potentiative interesting CFT you constructed through the nonlinear store model, which is a non-renormalizable Lagrangian. And then you may wonder whether a renormalizable Lagrangian description of the CFT is possible, such as a gauge state description. Let's try it. And to have such a description, there are a few things that we need to match. For example, we need to match the symmetry, we need to match the anomaly, we need to match the dynamics. But it turns out that this is very hard. And let's first just look at the symmetry and just focus on the continuous part. It has an SON cross SON minus 4 symmetry. This SON minus 4 is actually a bit special. And you call the case where n is equal to 6. This SON minus 4 is just SO2. It's just the U1 topological symmetry I mentioned before. And recall this SO2 didn't come as part of the flavor symmetry. It came from a rather non-trivial mechanism of flux conservation. Now, when n is larger, if we want to have this SON minus 4, you may wonder whether there's some generalization of the flux conservation mechanism, but we are not aware of any such generalization. Furthermore, you can just write down Lagrangians that can potentially have this symmetry, and soon you will realize it may not be hard to write down a Lagrangian with SON symmetry. It may not be hard to write down a Lagrangian with SON times n minus 4 symmetry, but it's rather hard to write down a Lagrangian with SON cross SON minus 4 symmetry that can potentially match the anomaly. This situation is a bit similar to the case with for supersymmetric theories with n equal to 2 and 3 and 4. We can also do some trial and error, and the natural candidates to try are the QED3 type theory or QCD3 type theories. And it turns out these theories are connected to Westminster-Witten theory on Grassmann manifold of this form, where G can be one of these depending on the gauge group here. And from this perspective, we can also see why the Stiefel liquids with n equal to 5 and 6 do have renormalizable Lagrangian descriptions. This is because of some rather non-trivial mathematical facts, namely the accidental isomorphism between the algebras. It turns out for n equal to 5 and 6, these two Stiefel manifolds happen to be also some Grassmann manifold, and then they fall into this class. But this identification pattern just stops here at n equal to 6. Then we also tried some other things, and we always failed, and we just conjectured that for all n larger than 6, the Stiefel liquids are just non-Lagrangian, meaning they are not mean field-like, or they are strongly coupled at all scales, or they are intrinsically non-renormalizable. I want to remark that this is a conjecture, and we don't have a rigorous proof of it, and it is also unclear whether it's possible to have a proof at all. Let me just mention some scenarios. The first scenario is, yeah.
Sorry again. Question earlier. Let me just make sure. As you say, the anomaly that you write on the multiple class anomaly is saturated by the WZW term, right? But the WZW term you construct using the tricks that the topological defects of some theory. For example, there you call monopole, but I prefer to call instanton or hedgehog unless you speak at some gauge group. Otherwise, I would just call it instanton or hedgehog. And that's an SO3 breaking for the familiar example that traps the quantum number, fractional quantum number of the unbroken SO2 on one side. And you can use that to do the other side and try to construct WZW. So that's the similar things here for the construction for n larger n, right? So I suppose there is still some information about the monopole that you construct this WZW, correct? And that guarantee you to saturate the anomaly you write down for the Martu class. So it's not the monopole doesn't play any role for construction of WZW term. It should play a role, right?
And let's distinguish two types of monopoles. There is a monopole specific to the U1 gauge theory, that is the instant operator for this U1 gauge theory, where the U1 gauge field is dynamical. And you can also discuss the monopole configuration of, say, of this symmetry, SON global symmetry. For SON global symmetry, if you try to gauge it later, you can have some SON monopole, and this guy has this SON -4 monopole. The anomaly will encode non-trivial information about the properties like statistics and the quantum numbers of those SON and SON -4 monopoles. However, if you are talking about the instant operators of the U1 gauge theories, either for n equal to 5 or DQCP, or n equal to 6 or Dirac spin liquid, those are just some components of the n. I guess what you want me to say is that to match the anomaly, I need these Westminster-Witten terms, but those monopoles are really just the components of n. In principle, if I just don't have the Westminster-Witten action, this theory is already a theory there with a different anomaly. It just doesn't match the Dirac spin liquid and the DQCP.
Okay, maybe the case I'm saying is, let's just take the big capital N is in n equal to 5. Then I didn't really mention monopoles. I think you mentioned, so that's why I mentioned. But I'm saying the hedgehog or the instanton, that the topological deferred breaking the SO3, and that's a construction that you can have this hedgehog trap fractional quantum number of the unbroken SO2, right? Or Z4, and which you can construct WZW.
Integer, not fractional.
Oh, okay. Maybe there's a convention. That's fine. But you use that to construct the WZW. But here, I think you are trying to clarify there's another object you are considering instead of the SO3 and SO2. Here you consider the SO5. And that part, maybe I didn't follow what exactly is the monopole you mean. Yeah. If you can clarify, you can. Otherwise, I probably just missed what you're saying.
Okay. So say now n is just 5, then there's a continuous SO5 symmetry.
Yeah.
And we can try to gauge the SO5 symmetry and study the properties of the SO5 monopoles of the resulting SO5 gauge theory.
Yes, you mean gauge as a background gauge, right? Background.
Let's say background. Let's just not make it dynamic yet. Then then this anomaly expression tells us about the property of the SO5 monopole.
Maybe in more detail.
What I want to emphasize is this monopole, this SO5 monopole is different from the monopole of the U1 gauge theory or the instant operator of the U1 gauge theory. The instant of the U1 gauge theory is just some components of the n, and that monopole is some configuration of the SO5 gauge field we introduce when we try to gauge it. You also mentioned the hedgehog defect. The information of the property of the hedgehog defect can also be read off from this anomaly expression. That's part of the properties of the SO5 monopole.
All right. In that case, I will just rewrite the W4 of O5, which break down to W2 SO2 and W2 of SO3, right?
Exactly.
Right, but here you'll consider the larger symmetry. But maybe that's an example which we just recap. Maybe also good for the audience when n is equal to 5. That's the case. But when n is 6, you say maybe there's some subtlety of expression, but basically this still works. How is the WZW analogously construct? Can you say a few words?
Okay, I guess you are asking. So yeah, let me follow you. Let me follow your line of thinking. So for n equal to 5, you know, we can construct some special contribution of n that has some special quantum numbers, which can be reflected from the Westminster-Witten action. And now you are asking a similar question for n equal to 6.
Or n equal to 7 if you choose odd, whatever generalization.
Yeah, 6. for any n. I will answer that question in a slightly different but related way. So here, the theory has SON cross SON minus 4 symmetry, and now we can try to gauge this symmetry. And we will also introduce SON monopole and SON minus 4 monopole. We can ask about the properties of those monopoles, and this anomaly expression tells us about that. For example, this SON minus 4 monopole is supposed to be a fermion, and it carries some spinor representation under the SON. And this is the analogous answer to what you wanted to ask.
How about the construction of WZW term? Is there some principle? You say some WZW, but maybe how is that? Is that just obviously? Maybe it's not obvious to me.
I guess your question is your question is really asking about the connection of this construction of Westminster-Witten and the physical properties reflected in this Westminster-Witten action. Is it right?
Yes. For example, can you write down some non-renormalizable Lagrangian for WZW and what the expression? Maybe you already write it. Maybe it's obvious. Maybe it's just the NDN that you write earlier.
So here I showed you the expression of the Westminster-Witten action. And I didn't write down this Westminster-Witten action based on some physical input, like how those defects will transform under various symmetries. I wrote it down just based on this target space. So to write down a Westminster-Witten action, the only input is just the target space. In other words, the construction of the Westminster-Witten action is purely mathematical. But from the Westminster-Witten action, for example, we can figure out something like the anomaly, and we can figure out some physical properties of those defects.
Okay. Yeah, I shouldn't take too much time. Maybe, yeah, you can go ahead.
You can ask later. Okay, so here, there are 2 other participants. One wanting to ask questions.
Yeah, just maybe a really stupid question. In the previous slide, when you write down the anomalies, I noticed that you don't have a W2ON square term. So maybe that's related to, like, as you mentioned, that there's a fermionic statistics for the monopoles, because I could imagine, like, on a boundary, you trivialize W2ON, and that gets you a spin structure, and maybe that's related to what you were saying. But I'm just wondering, like, you know, there's a imbalance, or rather, like, it's not symmetric, I guess. Yeah.
No. I guess you are asking why it's not.
Yeah. Why is it not?
It's just not. I don't know
why. Okay, so I guess it comes from doing computations.
Yeah.
Like how do you do the computations? Like anomaly matching, or is it like a mathematical formula or something?
It's more like anomaly matching. So it's actually here we were actually lucky. In general, it's very hard to obtain such anomalies for Westminster-Witten. Here we are actually lucky because we have this cascade structure, and we know for the theories with smaller n, what's the anomaly is spread in the literature. Then it turns out magically if we just have some write down the most generic expression that anomaly can be, and we require it to match the known anomalies for the smaller n cases, it turns out this requirement uniquely fixes this anomaly.
Okay, I see. Thank you.
Sure. Okay, so here I mentioned we conjecture that all Stiefel liquids with n larger than 6 are non-Lagrangian, but this is a conjecture. If it's true, it's interesting. Even if it's not true, we believe we need to have some new ideas to disprove it. And in that way, we can also learn some new insights of field theories. That's also good. So some scenarios include maybe there will be some renormalizable Lagrangians with smaller symmetries that can flow to center.
Yeah, so can I just to make sure I understand the so the statement that that you can't imagine getting this Wess-Zumino-Witten model from some large mass expansion of a Dirac fermion with some gauge fields that if you integrated the fermions, you induce this particular Wess-Zumino-Witten term.
And then?
No, is that a statement?
That's not the only statement. So if we do that, suppose we do that, we will first introduce such Wess-Zumino-Witten theory, and the Wess-Zumino-Witten, the nonlinearizable model field is still coupled to the gauge group, to the gauge field, and there's further work to do. But after all, we just cannot obtain this Stiefel liquid.
No, it's based on trial and error, and you can't get it, or you have a general reason that you can't get it by integrating out some Dirac fermions.
It's based on trial and error.
I see. Okay, great, thanks.
So there are some scenarios. One is we may have some renormalizable Lagrangians with smaller symmetries that can flow to the Stiefel liquids. Or maybe the symmetry of the Stiefel liquids is also not SON cross SON-4, but even larger, meaning they flow to some renormalizable stages with even larger symmetries. These are all possible, but all non-trivial to show. Even if we can show these scenarios or even others to disprove the conjecture, I think we will learn a lot. And I would like to compare this situation with the situation in the study of fractons. So Joan Ha in this paper used this lattice Hamiltonian to study fractal physics, and this lattice Hamiltonian has all its advantages and disadvantages we mentioned. Later, people started using some unconventional field theories to study the fractal physics, and this is still a very popular ongoing research direction. Now here we are constructing the Stiefel liquids using this non-renormalizable model, and there may be some other description or not, but it's interesting to explore. Okay, let me recap. So the DQCP and the Dirac spin liquid are unified as two simplest members of the infinite family of Stiefel liquids, and Stiefel liquids they have extraordinary properties like the symmetry, cascade structure, anomaly, and so on. And in particular, they may be non-Lagrangian quantum critical states. And along the way, we have seen that this non-renormalizable model formulation makes many interesting properties more manifest, including a simplified understanding of the centralization mechanism, a simplified understanding of the cascade structure, more precisely the relation between Dirac spin liquid and the DQCP. And there are also some others discussed in our paper. Okay, finally, I would like to discuss the problem of emergibility of these Stiefel liquids. That is, we want to ask whether, for example, the n=7 Stiefel liquid can emerge in the triangular lattice in one-half system. So more generally, we want to ask giving a low energy state, whether it can emerge in some specific UV setup like some lattice model. The usual approach to answer such question is to use the mean field framework. We design some either conventional or parton like mean field. If such a mean field can be designed, then we believe such a state can emerge. But now, these non-Lagrangian states are conjectured to be beyond the mean field paradigm, then this approach doesn't apply. So we need to find some new approach. So we recall at the beginning, we already mentioned for a state to emerge in some setup, it has to satisfy the LSM constraints. Now we just go one step further and conjecture that as long as the state satisfies the LSM constraints, then it can emerge. This is again a conjecture. It hasn't been proved, but there's also no known counterexample. Furthermore, in recent years, people have realized that LSM constraints are related to anomalies. In particular, for example, in this triangular lattice spin-1/2 system, the LSM constraints can be captured by anomalies of the symmetries of the system. And the symmetries include spin rotation, time reversal, lattice translation, and so on. And schematically, the anomaly can be written in this form. Basically, this just means, so the first factor means we are considering a spin-1/2 system, and the second factor tells us where the spin-1/2 system is located. For example, the first term tells us inside each unit cell there's a spin-1/2. The second term tells us at each inversion center there's spin-1/2. The third term tells us on the reflection axis there's an effective spin-1D spin-1/2 chain which has its own LSM anomaly. So it can be captured by the anomaly. Then we have this hypothesis of emergibility, that is, the emergibility is equivalent to, is conjectured to be equivalent to the anomaly matching condition. More precisely, suppose we have some L theory with some emergent symmetry GLR and L anomaly WGLR. We want to ask whether it can emerge in some UV setup with microscopic symmetry GUV and the LSM anomaly WGUV. Then what we need to do is to identify a symmetry embedding pattern or a group homomorphism from GUV to GLR such that the IR anomaly can be pulled back to precisely the UV LSM anomaly using this group homomorphism. And we can, for example, apply this to n=7 Stiefel liquids with such GR and WGR and specify the UV setting to be triangular lattice spin-1/2 system. And after some trial and error, we could indeed find such a symmetry embedding pattern. You don't need to read it through. Here is just to show you that it can be written down. Here, this N is a 7×3 matrix, and you can see spin rotation rotates the first 3 rows, and for example, translation involves both left and right multiplications. And this symmetry embedding pattern works for the anomaly matching. Then, from this perspective, we come back to this map. So initially, we said this DQCP can arise as a critical point between collinear magnetic field and the VBS, and Dirac spin liquid can arise as a critical phase, which can be a parent state of non-collinear magnetic field and the VBS. Now we are arguing the n=7, the possibly non-Lagrangian Stiefel liquid can also emerge on the triangular lattice spin-1/2 system as a quantum critical phase. And using the symmetry embedding pattern, we can also figure out what's the symmetry breaking pattern in the 2 ordered states. They are these ones. And it turns out these magnetic orders have been identified in some numerical studies previously. This means if we explore the vicinity of the phase diagram of these models, maybe we will end up with the interesting non-Lagrangian state. And a smoking gun signature for this state is an emergent SO7 cross SO3 symmetry. Namely, more precisely, you will see 21 operators that all have parallel decaying correlation functions, but with identical decaying exponents. This is a remarkable prediction, and you usually need some rather non-trivial mechanism to have the to have identical exponents. Yeah, Juven.
Yes. Oh, by the way, please take your time. Question is about, can you comment about the critical point or critical region? And if it's a critical region, what are the order of the phase transitions? When you draw those region, can you say a bit more? Is it a continuous transition also jumping, going through the two critical points?
Okay. Here let's distinguish two concepts. The first concept is if we impose the full emergent symmetry to the effective theory, whether the theory is stable. The second is if we put this theory on some particular lattice system where the symmetry is only the microscopic symmetries of the lattice system, whether the system is stable. By stable, I just mean whether it has 0 or 1 or 2 relevant perturbations. So from the numerical studies, the n equal to 5 case, the DQCP doesn't seem to be a unitary CFT. So maybe for now, let's not talk about that. For n equal to 6, it seems to be a CFT, although I have to apologize, I don't remember the evidence. It seems to be a CFT in the sense, also in the sense that there's no relevant perturbation that's allowed by the entire emergent symmetry. Now it's a more non-trivial statement saying that if I put it on a triangular lattice, because now we have a smaller symmetry and we will have more allowed perturbations, it's a more non-trivial statement to say that with the new perturbations, it's still stable. But you can figure out how the symmetries act and figure out which perturbations are allowed, and there's still evidence that this is a stable critical phase, meaning there's no relevant perturbation. For n equal to 7, now because we are not really able to handle the L dynamics, meaning we do not know the scaling dimensions and so on. So when we say this is a critical phase, it's really also a conjecture based on two things. The first thing is if we impose the entire emergent symmetry, it's not expected to have relevant perturbation. And this is already a conjecture. The second is from this symmetry embedding pattern, actually, you can see the most obviously relevant perturbations are disallowed. These perturbations include terms proportional to n, as well as the conserved currents under the emergent continuous symmetry. And then it's a further conjecture that it's a critical phase. Does this answer your question?
Yes, I think so.
Okay.
Thank you. But just make sure, at least I get the point, is that you try to study the perturbations, whether they are relevant or not, and see whether, suppose you start with some critical point, can it expand to some critical region? Is that one of the points? One of the the two things that you mentioned.
Yeah. So eventually, the stability on the lattice boils down to the question whether we have 1 or 0 or 1 or even 2 or even more relevant perturbations allowed by the microscopic symmetries. So if we have 0 relevant perturbation allowed by the microscopic symmetries, it's a critical phase. If we have precisely 1, it may be a critical point. If we have 2, it's a multi-critical point, and so on.
Sure. Okay. Thanks.
I also would like to use this cartoon to advertise this method of checking emergibility. So previously, people invented the mean field method to check the emergibility. That's a very powerful framework, and it could take people to many places. Later, people invented this more powerful parton type mean field theory. It could take people to states that people couldn't construct before. Nowadays, we are proposing this anomaly matching-based method, and it may really take people to some really unexpected states in some really unexpected way. And this is supposed to be a cartoon of quantum teleportation. I think it means we can send something from one place to another, which is separated from the original one by many galaxies. Okay, this is my summary. So the Stiefel liquids are proposed as possible non-Lagrange generalizations of DQCP and Dirac spin liquid, and we discussed their symmetries, cascade structure, anomalies, and so on. And we proposed this hypothesis of emergibility based on anomaly matching, and we used it. We argued that the some of the simplest non-Lagrangian states can emerge in the vicinity of some intertwined orders. Thanks.
Thank you very much, Liujun. 非常感谢Liujun for the nice seminar. Thank you very much. Question from the audience, please. If you can raise your hands, that would be great. If you cannot wait, you can just ask.
So there's no question.
Yeah, people shouldn't feel shy to ask.
Sort of have an open-ended question. Are there any prospects of generalizing to higher dimensions? Like anything we can do in 3D, like DQCP, like stuff?
We don't know yet.
You mean DQCP alone, or just also for non-Lagrangian? DQCP, I think people study, including me, but in 3+1. But if you're saying non-Lagrangian, I'm not sure people did this yet.
I think the 3D generalization of the DQCPs will have the normalizable Lagrangian descriptions, right? There are all kinds of gauge theories.
I don't know example of a non-Lagrangian DQCP in 3+1D type of story like what Liujun say today. But certainly there should be candidate DQCP-like behavior in 3+1.
Yeah, we are mainly thinking about 2+1D. Maybe a lesson is, in principle, there can be non-Lagrangian states. Not everything has to be described, has to have a description in terms of the normalizable Lagrangians. This can also happen in 3+1D, but at the moment we, even without supersymmetry, but at the moment we don't have any kind of.
And hi, can I ask a maybe naive question? Yeah, about when you make the comment on the non-renormalizable theory and renormalizable theory, you give an example of this as spin equals to 1 on the square lattice, and you give two field theory. One is renormalizable and the other is non-renormalizable. Shall I understand that as a duality between them, or it's not a good perspective?
Duality is just a name. They are all descriptions of the theory. You can call it a duality. But I guess this duality, this particular duality, doesn't really bring us a lot of insights. Unlike the more non-trivial duality, the rather invisible non-trivial dualities.
I see. Thanks.
Maybe let me ask, maybe technical, maybe for some people who might know quantum field theory. So they are non-Lagrangian, maybe Soucy quantum field theory for sure. Also in 3D, 2 plus 1D, correct? In the literature in the past. I didn't do research for the 3D case, but I know 4D they are. So do you know those literature for the 3D non-Lagrangian field theory?
I think the most discussed non-Lagrangian field theory in the supersymmetric context is in 3 plus 1D.
Right.
Oh, it is in 5 plus 1D.
No, they are certainly 3 plus 1D or 4D.
But I'm not very familiar with them.
What I'm trying to say is that can you relate what you have for non-Lagrangian theory as some Soucy breaking of that type of non-Lagrangian theory?
Oh, I don't know. That's an interesting question.
Yeah, I don't know much about the example in 3D, but I think 4D they are. Anyway. Yeah, so if no more question, let's thank Liujun again for the wonderful seminar. Thank you very much. Thank you. 非常感谢. Thanks.
Thank you. Bye.